For the thousands in attendance and the millions watching around the world. From the capital city, ladies and gentlemen, let's get ready to rumble!
The famous Michael Buffer there introducing us to our afternoon revision session. Welcome everyone and thank you for making
Wellington
it.
Jigare is a man of many impressive
Hang on a moment.
accomplishments. He became the first player from Africa.
There we go. ESPN. Can I get one person or a couple of people to let me know they can hear me, please? All good? Okay, great. So I'll now, if you've never seen how the Discord share works, this is how I will try to do it, and hopefully we'll be okay. Alright, so you should see stream running, or you should see that I am live on the left, and then if you click on me, you should be able to connect to my stream. Okay, give it a shot. It's do you see there's a live next to my name?
Managed to go in.
Okay.
Which mode
Stream
is
loading.
Yeah, can see.
Perfect. Okay, great. Alright. So not quite Zoom. It's a little bit different, but the good news is we won't get kicked out here. The good news is it's not this is outside class hours, so no attendance, no nothing. Please do stay muted, everyone, if you're not on. The feedback here can get ridiculous. So no attendance, no nothing, no one needs to be cam on or anything like that. Like I said, this session, welcome those of you from all the various cohorts. I think we have representatives. This will not be anything new, so no secret sauce. I'm not going to disclose anything here that we haven't either talked about already or that you will be talking about soon in your classes. This is purely for revision. Agenda up as I posted in the morning, and so we'll cover our basic DL modules. We'll go on through the rest. So hold your questions for me, please. Segment by segment. I mean, I will take questions, and I am glad to do so and happy to answer them. But let me finish my segments, and then I'll very regularly, every 5 or 10 minutes, try and check in and pick up your questions. You can drop your questions in the chat at any time, and then I'll be happy to pick them up as we go. All right, so let's get started here. So deep learning, although it is regarded with a lot of trepidation, a lot of hesitancy, a lot of people are scared of it. None of you in any of your 3 cohorts should be, because as we can see from this diagram, which again should be very familiar to all of you, AI, if AI is our big bubble enclosing every possible approach for trying to get machines to think or trying to get objects to do something, then we've tried various approaches in the past. I'll talk a little bit about symbolics, constraint of time here, so we'll be on a bit of a rush through the history section of Module 1. I'll talk a bit about symbolic. And then all of you have experienced machine learning already, because I know for a fact, I checked all your schedules, every one of your 3 cohorts has finished the machine learning module. And deep learning is simply a subset of machine learning. So for those of you from my cohorts, I have beaten this into you again and again and again. Here today, this is Tom Mitchell himself with his book, and it occurs very, very early on, I think in page 4 of the official manuscript. There it is. Can everyone see it? Yes. Our literal textbook definition of what machine learning is, right? And so in machine learning, we have some task that we want the machine to do. This task can generalize to anything. Here, Tom specifies, Professor Mitchell says playing checkers is one task, recognizing handwriting is maybe another task, but always, always, always we have this definition here, and we should come back to it because it is important and it does help us. So particularly for those of you in the ML SCTPs, you must know the definition of what you are doing as a profession. Learn this definition of machine learning. I mean, this is literally the machine learning textbook, right? So what is T and P and E? Let's talk about that first before we get back into DL. So, oops, where am I? So a task, as mentioned, is, okay, I'll go back to the example, actually, I think that's better. A task is anything we are asking the machine to do. So if we could be asking the machine to play checkers, or play chess, or play Mario, or play Dota 2, or any number of video games, or board games, or we could be asking it to make predictions, or do calculations. There's all sorts of T that we could be asking it to drive a car, or pilot a spacecraft. Many things that T could be, right? So T is just what we want the machine to do. P is how well the machine performs at T. And it is very important that P be quantitative. Why? Because we want a precise measurement of whether the machine is improving or not as we keep attempting to train it, as we keep hoping that it learns. So yeah, I think it did a little bit better, is not good enough. Or, it seems a bit worse today, is not good enough. We want a quantitative metric, like, oh, we saw a 0.17% increase in accuracy here. Or, oh, validation loss seems to be improving, it's just 0.05 today. Right? So quantitative measurement, very critically important. Next, we want, or rather we define E as a unit of experience that we hand to the machine, or we expose the machine to. So in this checkers learning problem, E is playing more checkers. In this handwriting recognition problem, E is reading more letters. In driving a car, E would be, experiencing what the input would be like for sitting in the driver's seat, right? So E, again, just like T, takes various forms. It takes forms, that are appropriate to T, but the notion is that as the machine experiences things, it will learn. So this is very analogous to how human beings learn, which is the first trap I want everyone to be aware of. It is not the case that for a particular unit of E, the machine will learn as well as a human learner would do. For example, you could probably take a child and put that child in a second language class, and by the end of maybe, 3 or 4 lessons, that child could probably say hello, could probably count from 1 to 10, might be able to write a few simple things like their own name. The machine may not do anywhere near as well as that. The machine might get some equivalent of, 0.5% of P out of the same unit E that a human being does. The advantage that the machine has over a human learner is that the machine is able to scale E at a rate that humans cannot hope to match. So if we want a machine to be able to know the canon of published works in the English language, the machine is able to ingest all of that data, all of those books, all of those authors, within a matter of seconds. Whereas it would be a matter of years, probably, for a human reader to read every published work in just English. And then if you add in published works in other languages, it becomes almost impossible to do it in a human lifetime. Whereas a machine can probably knock it out in a day or 2. So this is, the foundation of ML. And now let's transition into DL. We'll talk about how DL is different or distinct from ML. You all have probably seen, I know I show this in Flickfits on my cohorts all the time, this Asimov Institute neural network zoo. So let me zoom it out actually. So, we have a variety of networks here. We'll come to them in a moment. They are all attempts at recreating or replicating biological neural structures. So in the human brain, we have these neurons and they interconnect to each other, and the system of synapses or interconnections, this is believed to be what gives rise to human intelligence, memory, creativity, etc. So similarly, by building a relatively complex network with a proliferation of connections, it was hoped that we could see progress in machine learning through this construct of a deep learning analog to what a biological learning structure was. But as you'll see in Module 1, it actually took quite a long time for that to happen. let me bring up, our slides here. So again, not NTC lecture, so I don't have to worry about NTC rules. So I'll just do this, and we'll keep going. We don't have to worry about slowdown. So time-wise, I planned for this to be 2, possibly 3 hours. I'll try and hold it down where I can. I'll try and cover just the essentials. So we will go through everything, but we may not go through everything, at the same pace that we did in class, of course, because this is basically like just a morning session or just an afternoon session. So history of AI I will run through again, but we will do it much, much faster than we did in class 10. So brief history of computerized AI. Here is this timeline. AI, just like many, many other fields of endeavor, has booms and busts. You all probably remember fields like biotechnology or chip manufacturing that have had booms and busts in our country. And other fields have had booms and busts everywhere else. So here in the bottom timeline, we see the first AI boom from the invention of the Turing test in 1950 up until that first AI winter in 1973. Then there is a bust from 73 until 80, boom again from 80 to 88, long bust until 2012. And then in 2012, something special happened that kicked off the recent and ongoing boom in deep learning in particular, and also AI in general. What do we mean by boom? What do we mean by bust? It is exactly what you might think it means. It means that there is money and interest in the field. So if we consider there to be, say, this virtuous trinity, and let me establish here a virtuous trinity. So our virtuous trinity consists of 3 entities. We have Big Daddy government, and when a field is in boom, government hands all that money down to academia. What is academia? It's your system of universities, learning institutions, that sort of thing. And because of this new influx of government largesse, academia is able to do things like endow more chairs of professorship, open up new schools, offer new scholarships, offer new programs, all in the field that is experiencing the boom. And then the result of this, of course, is hopefully good primary research, as well as, of course, if you've gone to school, trained talent. And this research and these trained talents, they benefit our third rung here of industry. And industry can take research and turn it into products and services. They can make use of talent emerging from academia to work in new and emerging fields where skill sets might be rare, like AI and deep learning. And then industry, of course, is meant to close the loop here by paying tax back to the government. Although these days, not a lot of tech companies do that, because I think their tax lawyers are probably better qualified and better paid than government tax lawyers. But this is how it is supposed to work for a field that is in a boom time. For a field that is in a bust time, this part disappears. And when this part disappears, then all the rest of it starts drying up. If there's no money to go to school for it, then parents don't tell their children to go to school for it. You get discouraged from doing it as a PhD. No new programs come in, enrollments drop, etc. And then this rolls onto industry, rolls onto government, and it is again a long self-defeating loop. So AI at the moment is in a boom, especially in this country, which is, I know, why a lot of people take the SCTP. This upper chart, don't worry about. You can read that in detail at your own time. So this slide, when I wrote it, it was just to illustrate that people have always thought about getting machines to do stuff for them. So here's Talos, a Greek myth. Here's the Jewish golem. But let me skip ahead. Here is Alan Turing. And Turing was a code breaker at Bletchley during World War II. He cracked the Nazi machine Enigma, being a huge contributor to the Allied war effort. His reward for contributing to this Allied war effort is pretty shameful. You can read about it in history. But the big contribution there is the Turing test. The Turing test if we look at it, is the layout of 3 participants. Yeah, Wikipedia's image is fine. 3 participants, a human judge C, a machine participant A, and a human participant B. And to not prejudice the judge against the machine, Turing stipulated that both A and B should be behind a wall. And so, behind this wall and only able to communicate via the written medium, C could ask questions freely out of A and B. A and B were obliged to respond to the questions of C. And a machine was said to pass the Turing test if its responses were so good, so high quality, so human, that C was unable to distinguish between A and B which one was the actual human being. We've seen lots of advances in that since then. I've shown a video to my cohort, but in the interests of time, I'll just drop the link for everyone who is in DA.
Let's say,
Here we go. Okay, so this video you can all watch on your own time if you've never seen it before, but no, people have probably seen it before. All right, let's back to lecture here. Okay, and so this was Turing's big contribution. Here at the Dartmouth Conference in 1956, the taps really come on in government for this part. So money is in, lots of money, so we get lots and lots and lots of this. So you can imagine that there is tons of money in the field. And why does this happen? The big motivating geopolitical event at that time is the Cold War, which kicks off between the winning allies of the Second World War, because one of them was communist and one of them was capitalist. That was the USSR and the United States and its allies in NATO. So lots and lots of funding for AI, and around this time we see a lot of very, very early breakthroughs in the theory behind AI. So we discover McCulloch-Pitts come up with their perceptron, Rosenblatt refines it later on, and we see developments of things like ELIZA and this Arthur Samuel checker plane program. Let's talk about these conceptual developments. So here, these fundamental building blocks, these essential core components out of an ANN, any ANN, right? You can see all of these here. All of these green things, and this is a build-up of a green thing. All of these are the the foundations. These are like the bricks or the essential small Lego that we use to build these neural networks. And so the what are they? What do they do? McCulloch and Pitts in 1943, they proposed that they could create this McCulloch-Pitts perceptron, and it would be able to take in some input, and then it would be able to weight that input. That is, the input would get scaled by some value, and then there'd be a summation of these various inputs, and then that summed value possibly might trigger an output in their neuron. This is very, 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 very close to what the final design in most neural networks ended up being. But they did leave out a key component here. And that key component was supplied by Rosenblatt later on in 1958. And if you see it down here, it is this component. So the Rosenblatt perceptron is almost identical, actually, to the McCulloch-Pitts perceptron. But what he added was this notion of feedback. So as the model trained, it was able to learn. And this was a key breakthrough. This is what enables learning in DL, and it's a genius concept. Also, sadly, a concept that was literally ahead of its time. So when you can see here, this is from Rosenblatt's original paper. this is not a symbolic drawing. This is literally a bit of card, and these are actually wires that he used to string these things together, because remember, in this era, it was very, very, very hard for a researcher to lay hands on something like an integrated circuit. That would have been, out of the realms of imagination for him. So he had to make do with this sort of thing. Because of the limitations of the physical hardware, and because academic jealousy is, ever abundant in the academic field, his fellow researchers turned on him. So here's Marvin Minsky of MIT, and with his co-author Seymour Papert, he wrote this book, Perceptrons. And don't let the title fool you. Perceptrons is just a long attack on perceptrons. You can read it yourselves. It's very, very dismissive. It rubbishes the perceptron because of its inability to do certain things, again, because of that hardware limitation. So as a result of this, as well as this, we head into the first AI winter. This is Sir Michael James Lighthill releasing the Lighthill Report. He was asked by the UK government to say to survey the field of AI and see what he felt the outcome had been of this 20 odd years of government spending on both sides of the Atlantic, in the US and in the UK. And Sir Michael is a very reasonable, very objective, very straightforward person. He was a mathematician, he was an aerospace designer, and he did take a fair look at the field, and he did fairly report in 1973 that the state of the art of AI in 1973 was that most AI was impractical, unworkable, most researchers didn't have basic research skills, and that the whole thing was a big waste of all of that money. And so owing to this, owing to perceptrons, owing to the general failure of the first boom in AI to achieve anything substantial, we head into AI winter. And in the first AI winter, like I said, everything sort of got defunded, not much goes on. But the first AI winter doesn't last that long. It's just from 1973 until 1980. And then in 1980, Ronald Reagan wins his election to the US presidency. What he's holding there, this is a joke I squeezed in. This is a block of government cheese. Government cheese is a dairy substitute product, I think is the official phrase. And it's made of cheese residues from the cheese making process. So it isn't real cheese. It's not even real processed cheese like the sliced cheese that you can buy at NTUC. It's a cheese-like substance. But it is enough to hold body and soul together. It's a good survival ration. The US has millions of tons of this stored in bunkers, all over the continent. And it also serves as a slang term because government cheese, in plain meaning, is this stuff, right? It is all of the funding that comes out of the government. And when Reagan came back in, that funding tap was opened up very, very wide, not just for AI, but across many fields of science and industry. Why? The reason is Reagan, I really do believe this, on a deep personal level, I think he hated communism, which sounds silly to say, but he did really hate communism. He didn't hate the communists, because I know he had a quite warm, friendly, personal relationship with people like Gorbachev and his other associates in the Kremlin. But he was determined that the US finally win the Cold War, and so he opened spending on a wide variety of fronts. So you can read about things like Reagan's Star Wars, which was a plan to put lasers in space to shoot down Soviet missiles. And on the AI front, he thought, why not? This might help as well. So huge spending in AI, but not the machine learning that all of you have learned up to this point so far. This, in the 1980s, is where we are in the small purple bubble of this side lane of history, which I'll talk about briefly, very, very briefly. What happened with expert systems was the notion that if only we could program a machine with enough rules, then by stacking enough of these rules together, then the machine would be capable of handling any particular... Actually, I'm going to mute Discord because people are locking in and out. If I suddenly lose audio or anything, please drop me a chat. Okay. what happened is that if you had this notion of that the expert system could receive enough expert programming, if it could receive all of these rules and all of these guidelines that any practitioner in a particular field, like medicine, like finance, like oil discovery was a big one, then the machine could then be turned out onto production, and it would serve as a replacement, expert with no need for salary, no need to be fed, no need to sleep, etc., etc. This failed for many reasons. I'll talk about some of the reasons. One of the reasons was this was the 1980s, so if you remember, technology had still not got up to a point where it was, exactly impressive or substantial. So this is again that era of 8-bit computers, of still soft floppy disk drives in many cases, very, very severe limitations in compute power as well as in storage. One thing was a hardware shortage. The other thing was the notion of trying to build a system through rules fails very, very quickly. So the quick example I give for my classes, for those of you in cohort 25, is that say we take something like this. That's what I usually use. Alright, so say we take this guy, and good thing we ran this class after lunch. So say we take this guy, and we want to build an expert system that can enumerate enough rules that we can easily, clearly, with very, very high accuracy, identify this thing all the time. And it turns out that it is actually really, really hard to do it. So, in class I played the game with everyone. I was like, give me one rule at a time. And people say, okay, well, what about claws? And then I pull out a praying mantis. And I say, okay, so by our rules, this is a lobster. And then they say, okay, well, what about it lives under the sea? And then I pull out a crab. And then so on and so forth. And then they say it's blue. Then I show a cooked lobster. The point being that there are so many edge cases or so many special situations that occur when you are trying to make a decision or make a determination about something, that it is actually wrong-headed to go about it from the perspective that you can just feed the rules to the system and then the system can make the determination for you. In ML, we have given up on that completely. So let me show you this old slide here from the retired version. So the notion was that the data was there, and then we would provide this programming or this rule set, and then with the benefit of our programming, the computer could make the correct determination about the data. We have given that up completely. No one is attempting to do symbolic AI at any serious scale anywhere these days. We are fully in this machine learning domain, and you'll see what's swapped between the top diagram and the bottom one is that program and output swapped. So we feed in data, but we have already, worked out which data is which. So this is the labeling component. So, we put images in appropriate directories, or we put the real value of the regression in a column in a data frame. The machine already has the answers. And so with the raw data as well as the answers, we let the machine do pattern matching on its own, which it is much better at than we are, and then it comes up with its own program. And this is by and large the approach that people use today, and this generally is what works better. That is an important point, so I will pause for questions here. I did unmute the Discord, so you can either hop on Discord mic or type something. Questions so far? All okay? All right. Right, so that's a distinction between expert systems and ML. Not that I think any of you get tested on expert systems, but good to know about. Good to know about the history of your industry. While all of this is going on, this is a Symbolics keyboard, the Space Cadet, which you can buy on eBay. A lot is happening in foundational ML. So backpropagation is invented in 1986 by Hinton, Rumelhart, and Williams. Keep Hinton's name in mind because it will show up again very, very shortly. And then we get a lot of progress in NLP. So aside from inventing the word corpus and token, they also do stuff like work on the tokenizers and the embedders and all of this other stuff. Also, other things happen in the 90s, such as when we move into the second winter after the end of the second Reagan term. Everyone realizes the expert systems are fragile, they're brittle, they don't work well. Neural networks still not there because this design that Rosenblatt came up with at this point 26 years ago, still cannot be achieved by early 1990s technology. So everyone gives up on general AI, the notion that you could get a Skynet or a Wintermute, for those of you who are William Gibson fans, and everyone switches instead to narrow AI. So we'll give up on having an intelligent virtual companion you can talk to and have discussions with. Instead, I just want an AI that will tell me if this tomato is ripe or rotten. And, this sort of similar thing. Also in the 90s, all sorts of stuff happens with everything you all covered in ML. So a lot of the early papers for things like decision trees, like K-means, like SVM, they all published between 1988 and 1999. Here is a failure of an early system. The upshot here, I'll let you read it on your own, is that the army, when it is training this tank recognizing system, when they reach the point where the tank recognizing system actually detects a tank that is completely concealed, they realize that, oh wait, no, we've actually been always training with the tank out at non-training time when it's ready to pose for our model, but then the tank has to go off for training at a certain other point in time. So all we've done is built a system that can tell the difference between morning and afternoon based on the sun position. Nothing to do with tanks whatsoever. This concept is called information leakage. It is also a problem that occurs quite often in ML and DL. Okay, so this is how DL kicks off. And this is all the stuff that happens. I'll let you read that slide on your own. Here's Dr. Li Feifei. She builds a huge image data set of 3.2 million images. There's 5,300 odd classes in this image data set. And when she runs it as a competition, no team can do very, very well. So here's the results of the competition. The paper comes out 2009. ImageNet is a competition in 2010. This axis here is the years, so 2010 to 2017. This is a scale of errors. So you want to be further down on the scale, close to the perfect side. You don't want to be up here where your system is making lots and lots of errors. First year, no one does better than 25%. Second year, also, no team, I should say, not any individual, no team does better than 25%. And remember, this is the 2010-2011 teams out of Microsoft and Google and Facebook and NVIDIA. So these are some of the best AI programmers in the world. Cannot crack this problem. But this team does crack the problem. Coming out of the wintry depths of Toronto, Hinton, here's his name again, leads at this moment a department at the university. Here's his graduate student. You should put Ilya's name in Google as well. It will pop up a lot of hits for you because he went on after this to have a very prominent career in OpenAI as well as other companies. He was working on ChatGPT until very, very recently. And here's Alex Krzyzewski himself, who was an undergrad at the time. This team named their network AlexNet. It is a double CNN. We'll talk about this when I get to the Module 3 section. And they absolutely smashed the competition, and this is what kicks off the current boom in AI. So here is that University of Toronto team absolutely destroying everyone else. The graph for this, by the way, comes from an amazing article, which I can link for all of you here. This one. So it's a really, really good read. Again, we can't cover all the details, but like I said, this graph comes from this article. Very, very, very worth reading. Let me come back. And so, with the Toronto team absolutely smashing everyone else, immediately the year after, but a lot of stuff happens. Google recruits Krzyzewski right out of undergrad. Sutskever gets a job, I think, with Elon Musk straight away. And then immediately, everyone else in the world starts to incorporate deep learning. Every leading team starts to incorporate deep learning. And just the very next year, practically the majority of the teams are able to cross that 25% error threshold that no team could cross, aside from the Toronto team in the previous 3 years. By the time we get to the end of ImageNet as a competition in 2017, all of these teams are using deep learning, and all of them do better than that 25% threshold, except for this team. I'm not sure who they are and I'm not sure what they submitted. How does this work in 2012 when it didn't work in 1962, didn't work in 1988? Finally, by this point, hardware has caught up to the vision that Rosenblatt had at the time. So in particular here, this GTX 580 is the GPU that the University of Toronto team used on AlexNet. They actually used two because they had two GPUs running. Here's a 4 TB drive, very typical drive that people use. So we can read the slide. A lot of what happened, a lot of what was criticized in the Lighthill report, in Perceptrons, none of these criticisms matter anymore, because hardware has progressed to a point where these designs, these very, very forward-thinking designs from decades ago, are finally actually able to be implemented. And the big push for this is, of course, the video games industry. It turns out that developing hardware that can create a 3D polygon and animate it at a 60 frames per second or better frequency is exactly the same kind of calculation that you need to do when training a deep neural network. Okay, there we go. So that's module 1. Let me just briefly talk through the background here, and then I'll do 2, which is very short. Then maybe we'll take a small break, and then we'll run through 3 to round out our session. So if you're building your own ANN, this is just a dissected version of what we have here on the zoo, right? So all I did was slice up this diagram. So it's just bit by bit. So we have an input layer. Why do we need an input layer? We need an input layer because we cannot feed data to the model in a format it will not accept. For example, the model will not accept something like this. This is an image, and the model doesn't take images, it only takes NumPy arrays. Everyone should remember NumPy from data analytics class. So we need to convert everything into a NumPy array, which involves encoding. Images, of course, they can be encoded. You can see here at the bottom left in GIMP, as I move my cursor around, there's a pixel position given in X and Y. Any plane can be listed as a system of coordinates. And then any color that we happen to, find down here, this color, if we look at it on the color wheel, it is represented, there's various systems that we can use to describe what this color is. Right, here's a CMYK representation, here's this representation. But the primary way that we encode is in RGB, so red, green, blue values. So we have at every pixel for this image a tuple containing a value for red and green and blue, ranging from 0 to 255, and then we can encode that image that way. So, whatever we're feeding into the model, sometimes we're feeding in audio, sometimes we're feeding in other types of input. We first of all need to convert it into a format that the model will accept. First part, input layer. The next part here, this middle hidden layer. What happens there is that we have within each of these nodes our set of activation an activation function per node per layer. So going from layer to layer, the activation functions can vary, but within a particular layer, generally the activation functions are the same. I say generally because you can write special layers where this is not the case, but don't worry, you won't be tested on that advanced usage yet. So there's an activation function within. There's also a weight or a hidden value that the model will use, I should say, to adjust its input and determine whether or not it gives output. You will notice going from layer to layer in this green hidden layer section that from each layer, every node, every one of these green balls is connected to every other node on the subsequent or the succeeding or the next layer. And this is why we call these networks FCDNs, or fully connected dense networks. And regarding how many layers we need to be deep, 2 layers is enough. 2 layers is a deep neural network. Then finally, once our model has done its calculations, it yields some output. For regression, this is fine because we just need some value. For a classification, we need a number of nodes in the output layer that corresponds to the number of classes that we are classifying. Why? Because your output will probably take some kind of format of, let's say there's 3 classes, right? You're trying to build a CNN to distinguish between apples and pears and carrots, your model will come up with a set of values, and then these values, what is that? That's 38, so say 60. These models, 61, let's say. These models will then come up with a set of probabilities. So say apple, pear, carrot. So the highest probability will be the carrot result. To accommodate these three probabilities, we need a node to represent each in the output layer, except for one special case. The one special case is if we just have two things. So if we're just trying to do two things like dog or cat, it is true that we could have one node for dog probability and another node for cat probability, right? Two nodes. That is one way we could do it. But we could also get away with just doing one node for cat probability. Why? If this one node doesn't hit 50%, then we know it's the other case, right? So just for binary, just for the case where we're only doing two classes in our classification, you can use either one or two nodes in the output layer. For every case where it's three or more, you need equal nodes in the output layer to the number of classes you're classifying. And we'll see this again in a little while. Okay, so let me skip that activity. All right, so what happens in the neural network? We have a feed forward phase. The input goes in, the weights and the weights get multiplied, it gets passed on if the activation function triggers, and this happens, layer by layer by layer until we get to the output layer. I said if the activation function triggers. What is the activation function? Well, the activation function could be one of many things. Here are 5 different ones, but that's not all there are. There are lots and lots of activation functions. So on the Keras documentation page, by the way, I do encourage everyone to read the documentation pages for all of these libraries because there's a lot of documentation. You have many functions available. So you see here there are, what is that, like 16? So there's a wide variety available. Good news for all of you, you only really need to learn about 2 of them. The 2 you need to learn about are tanh, hyperbolic tangent, which used to be the old and popular one. The new and popular one is ReLU, rectified linear unit. So tanh, it just follows the tanh formula. You take the tanh of x, that's the value that triggers. ReLU takes this function, so it's 0 if x, it's the maximum between 0 and x. So if x is less than 0, it will be 0. If x is more than 0, it will be equal to x. So that's at y equals to x line on the right hand side. So you really only need to learn about ReLU for now, as people just being introduced to deep learning. Later on, you can acquaint yourselves with the rest of them. Okay, and then the input gets adjusted by the weight. Maybe the activation function triggers, maybe it doesn't. This gets passed down, and then finally we reach the end of the network, and either our model did a good job, as measured by our test set, right? Still machine learning, so we're still doing test train splitting, and we're still seeing how the model generalizes, or more likely than not, the model is probably in error a little bit. So when the model is in error, back propagation is what helps us adjust the weights. Remember, every one of these has a weight which gets initialized either randomly or some fixed value. In either case, that's not good. Randomly is not good for solving our problems. Fixed value is also probably not good for solving our problems, no matter what our problems are. If our problem is a regression, I don't think random values will be helpful, nor fixed values. Image classification, also not helpful. We need some particular values of weights that we need to discover, which is why we're doing this learning. So in back propagation, the error will be calculated, and then the adjustment will be propagated backwards through the network. The loss functions are a little bit complex, and they are derivatives. You don't need to do the calculus, but do know that since the chain rule applies, there are a lot of terms layer by layer that are identical. So in a big part of modern backpropagation, we don't calculate loss for every node in every layer in the network. It is done term by term. So say there's 2 terms in that loss function, right? And then we don't have any yet. Okay, in that case, there's no choice. Both have to be calculated. But then if we go back another layer, and we see that this layer passed down a term to this layer that has already been calculated, that calculation will be reused. So as the backpropagation goes backwards through the network, the model will only make those calculations that are absolutely necessary. Where it is possible to reuse a calculation, it will reuse those calculations. All right, and then the weights get adjusted, but the weights don't get adjusted all the way. They get mitigated or scaled down by some learning rate. Why? Really, what we're trying to do with the weight is we are trying to get the weight to hit the low point of this loss function. This is a gross oversimplification because this is a 2D representation. In reality, with the complexity of your data sets, more likely this will be some 17-dimensional or 2 million dimensional, imperceptible to human beings visualization, but we can take it to be the same thing. No matter how complex it is as a shape, still the weight needs to descend down it and reach the bottom. We take incremental steps, that is, we scale the correction and backpropagation by the learning rate because we don't want to overshoot. If it was just this, right, there's a possibility that here, let me snip that. So let's say we have let's say we have this going on, and we know what we know where the actual bottom is there, right? It's very clearly there. It's given to us by the test data set. We know it should be here. We do not do this with the model. We don't have it shoot straight down to that minimum point. Why? Because if we miss or we head in the wrong direction, which can happen, we might accidentally, that was not a straight line. We might instead find ourselves here, right? Bouncing on another side of the wall, still not anywhere near the bottom. And then we might bounce back again the other, bounce back again the other way. We're not descending incrementally, which is what we want to do, which is why there's that restraint of the learning rate. We'll see the learning rate later on as we look at building the models. And so this is our epoch, right? Our epoch is where we train the model on the data set. So we're gaining E in the ML sense. The whole data set is going to go into the model, right? It's been test train split. It's also been split up into batch sizes. Batch by batch, everything will be fed into the model until the whole training data set has been passed in. Once a whole training data set is in, we do a forward pass. Once the forward pass has been done, we look at the error using our test data to do that. We do back propagation to adjust the weights for the neurons within the network, again adjusted by the learning rate. We see whether or not we've hit accuracy or loss that we targeted. So this is something that you can do when you're programming these. The training of a neural network is you can say, I just want to train until 77% accuracy, or I just want to train until loss goes under 5%. So you are able to do that, but it's optional. You don't need to. So if this does happen and we do hit the targets, then we stop training. The other optional stop is we specify an epoch count for how many epochs total. So I just want to train for 10 epochs. Fine. It will train for 10 epochs and it will stop. Again, this is optional. So you could just keep training the model as much as you like. And there are so then assuming these two don't take place, the epoch will finish. We go up by 1 epoch. We go back to step 1 and then we keep training again, right? Because this is a cycle. If we don't make either of these stops, then the model just keeps training forever. And you are all aware of models that do this. You all know ChatGPT, that trains forever. You all know Gemini, that also trains forever. At huge cost, I should add. There's an article today about how much more Google has spent this year on data centers thanks to AI. I'll see if I dig that up in a minute. Okay, so that's our Module 1 recap. Module 2 recap should be pretty fast, actually. But, yes, go ahead.
Can I just put one question here?
Yeah, go ahead.
Is it correct to say each neuron has one activation function?
Generally, yes. So for all of our layers, that we are talking about in Keras, they are all
And
pretty standard, pretty regular things. So it is possible to
So-
build a special layer with more than one activation function, but we generally don't do that.
oh, okay. So one layer consisting of the neurons, and all the neurons have the same activation function.
In that layer, yes.
Is that correct?
In that layer, yes. But on the next
Oh,
layer,
so-
you could change the activation function.
Because we construct the architecture that
Layer by
use
layer.
another type.
Exactly. So it's shared on the layer,
Okay.
but on the next layer you can change it. I have an example of this actually. Here on, oops. Oh, it's here. In these notebooks, later on when we get to the main image, when we get to
It's
the
fine.
main,
I think I got my answer.
yeah, no, that's fine. But I did want to, it's a good question. So later on, when we're doing, we're going over this notebook, which will be near the end of the day. When you're building this model, for example, right? Here, you're not constrained layer by layer to be the same. Here, this happens to be the same activation, but if you wanted, as you go to a different layer, you could swap the activation. Great question, Kinsey. Any other questions? Anyone else I can help before we move on to TensorFlow? All good? Okay, give me a second. Let me shuffle the slides around here. Alright, so our next section is, well, that's 50 minutes. Our next section is TensorFlow. We'll talk about this, then we'll cover that basic TensorFlow notebook. Then I'll talk about CNNs, and I'll talk about both the image classification Canon notebook as well as the CNN extractor. And then that will probably do us for today. Okay, so TensorFlow. TensorFlow is here in this broad ecosystem of Python ML in rivalry with this beastie PyTorch. TensorFlow is by Google/Alphabet. PyTorch is by Facebook/Meta. TensorFlow, again, I know all of you have experienced this because all of you did the data analytics module already. TensorFlow is horrible to have to program with. It is very, very analogous to how we all showed you matplotlib in the data analytics module and then very, very quickly switched to Seaborn because no one wants to have to write raw matplotlib. Keras is that equivalent of Seaborn, and usually in most of my notebooks that I've given everyone, we are running Keras commands rather than TensorFlow commands, with the exception of a few touches here and there that I will point out as we go. So TensorFlow is machine learning library by Google, right? Because DL is ML. Very, very importantly, it is scalable, extensible, provides a lot of metrics accessible through things like TensorBoard, provides a lot of serving engine. So I know I introduced Gradio to quite a few of you. The professional grade serving is done through things like this. This is a production grade machine learning pipeline. So you'd use TFX and you'd build up this pipeline for training models, retraining models, storing models, retiring models, maintaining the versions, etc., etc. So yeah, here's a simple schema that they laid out down here. I'll drop this documentation because it takes a couple of weeks to do that on the professional scale. This is why Gradio is a wonderful library for just prototyping that service. But I am skipping ahead. All right, we'll come back here. So another important aspect of TensorFlow is that it has acceleration support. So GPU acceleration, absolutely critical in the field of deep learning. Absolutely critical. We'll see that in a moment with the image gen notebook. Sorry, the image classification notebook. Okay, that's TensorFlow. Generally powerful, but kind of unwieldy. Enter Francois Chollet. Because this is a recap session, I'll skip linking to Francois' Twitter. If anyone's interested in Francois' Twitter, please ask me. I'll be glad to link to you. The reason I mention it is, much like Ronald Reagan, Francois has deep and personal hatred, except instead of hating communism, he hates PyTorch and he hates Facebook. Sorry, the other way around. He hates Facebook first, I think, which is why he hates PyTorch. Anyway, Keras is a wonderful library, Francois' personal predilections aside, and very, very useful. And it gives us a lot of pre-built, predefined layers. So a big distinction, going back to what Kinseng's question of the one activation function per layer, right? So we usually, when we define a layer like a deep layer or something like this, we want, so core layer here, regular dense layer, right? We'll take one activation usually, right? The thing is, if you wanted something more complex than this, then you need to delve into the theory and the research of deep learning. So basically the equivalent is on this image, in this image, rather than using this set of Lego down here on the left to build up new networks down here, which is what we do in ML engineering. You are in the business of inventing the new Lego on the left, and that is what DL researchers do. And generally in ML, we are quite happy with the layers we have. We just want to be able to assemble them and deploy them efficiently, which is probably the biggest difference between Keras and raw TensorFlow and raw PyTorch. So in our applications, we are implementing models that we already know. We aren't creating new types of layers or inventing new types of activation function. So we are generally happy with the layers available to us thanks to Keras. If you aren't, which is not to say that you can't design new layers in Keras or TensorFlow. In Keras you can, but the big part of Keras is the convenience. A lot of you, like I said, I know you all took machine learning. I know I showed that graphic of DL being part of ML. So how is TensorFlow different from scikit? This slide goes into it in a little bit of detail. The big difference is scikit doesn't support GPU, so a no-go there. And that TensorFlow is really more focused on DL. You can't, for example, easily get one of the other scikit classifiers implemented in TensorFlow. If you remember from doing ML, we have a lot of estimators available in scikit, right? There's, I think, 200 plus at the last time that we talked about them. Oops, scikit down. Maybe this page is down, but hopefully the rest of it is still up. There we go. Someone's revamping the tutorial page. So in the API, right, there's all of these sections available for all of this stuff. So there's this huge section on regressors, huge section on decision trees, etc., etc. In TensorFlow, we are really just interested in deep learning and deep learning layers. So TensorFlow very specialized, very GPU accelerated. Scikit more for general ML that is not DL. Google Colab is a place where you can have access to GPU if you don't happen to have it available locally. So, I do happen to have a GPU available locally, an NVIDIA GPU, I should emphasize. We'll talk about that as well in a minute. I do happen to have a GPU available, and 12 gig is enough to train most of the stuff we do in the syllabus. But if you don't happen to have that, if you happen to running a laptop, for example, or you have an AMD GPU, you're not out of luck at all. You can connect to Google, and then on Colab, in fact, let me run this on Colab. So say we run this on Colab. One of the things that is available to us and available very, very easily is that we can access a GPU anytime. Here, Google is giving me one. But here, deliberately, since I did want to mention it, let's demonstrate that difference between CPU and GPU. So I'll let this runtime kick off. I'll also put my own runtime in a race with it. So here I have the same model that I ran a while ago, and you can see my training times. They are all down here. Right, so about 12 milliseconds per epoch. And the TensorFlow model should have gotten to the point now. There we go. Close that one. Where it's downloaded the data set, good, and it should be in training time. And here, oh, not yet. It's still normalizing. Okay. Oh, there we go. All right, here we go. And so 12 milliseconds, right? We will come back to this one, and we'll see where we get. All right. So jumping back to, that's 223. It's always the first epoch is slowest, but this is not the whole picture here. So Colab, one place where you can get access to a GPU. The other place you can get access to a GPU is Kaggle.com. And Kaggle.com, I should do this on Firefox, because Firefox is where my Kaggle password is. On Kaggle.com, you also have access to GPU. You get an entitlement of 30 hours per week, of which I have burned about an hour teaching deep learning this week. You also have access in Kaggle, in your Kaggle notebooks, to connect to the Kaggle datasets, which is a very, very powerful feature. So for example, let's say I grab, this one. You see here on the right, you have many, many options for connecting to datasets that are available in Kaggle. And you can at any point connect to any of the hundreds of thousands of datasets that are available, some of which are extremely high quality. So I would encourage everyone to explore both TensorFlow, both Colab and Kaggle. Both are good things to learn and good sites to have access to. Oh, good question. Okay, so as to whether or not you should buy a GPU yourself, it definitely helps. It definitely helps. It's nice to have, not to worry about that 30-hour limitation time. It is nice to, have it available and then do whatever you want with your own models. But it's not necessary, even for this course. It's not necessary even if you join one of the AI programs, like in Singapore we have the AISG group. Very, very often in the professional setting, you are not sitting on a machine that is running the GPU, because the GPU in the professional instance is huge, right? It's not a consumer grade GPU that sits inside a tower like mine is. It is a huge beast like the NVIDIA A1000, so you need a proper server installation and air conditioning and power and all of this other stuff. No one is sitting right next to that machine to do their coding. So it's always remote. You're always logging in with a laptop. MacBooks, for some reason, extremely popular. I know why. They're very well made and it's a nice interface. So you don't need to get one. My answer to that question. We can pause actually. Is there any other questions so far? Okay, so Colab, a good way to get GPU if you don't happen to have a GPU of your own. Kaggle, another good way to get a GPU if you don't have access to a GPU of your own. This is how we can go about, designing a model in Keras. Really easy because, all of these layers are predefined. We just have to put in our parameters for, what sizes, how many nodes, and then everything is set up for us. This is about 10 times easier than it was 5 or 6 years ago. It's a huge improvement in convenience and ease of use. I can sense my code's telling me what this is the easy one. This is the easy one, believe it or not. I'm sure it will get easier as we go, because this is still not exactly peak user friendly. So I think more and more convenience will come into the field as we keep going. You can, as you work with models, save and load them. I skipped showing slide 14 because the slide 14 code is outdated. So instead I'll show my notebook later, which has the correct working code. That notebook is also in the channel from this morning, so you can all download that if you like. 25 people? Is this for real? Wow. Okay, so as we train models, as we adjust the weights, as we adjust the biases, that costs GPU time, it takes a lot of effort. We don't want to have to do it again and again and again. So if you have trained a model to a point where it's very worthwhile, highly accurate, gives great results in testing, then you can take those weights of that model and share them, with your colleagues, your coworkers, etc. You can store it and archive it for yourself, etc., etc. A final thing in the TensorFlow notebook, serving inference. So, like I said, TFX is the pro way that you would do that, but it takes a while to set up a full TFX pipeline. The easy way to do it is in Gradio. And with Gradio, within about 30 minutes or so, less once you get acquainted with Gradio, you can just read the documentation and very, very quickly serve up a model. So here is a demo that they used to run on the main site. So that's my scribble down there. There's the Gradio model, identifying that as a bunch of grapes. There are many interfaces available on Gradio. So aside from sketch input, you can also drop images, you can write in a text box, you can use a slider to set some numeric value, you can adjust buttons to do some presets or use a drop down. Many, many things available. Okay, so let's talk then about that first notebook before I move on to the CNN notebook, and then we'll wrap for our revision. So in this first notebook, the M2A1, which in the general channel you can download. I put it up at 11:45 a.m. My cohorts, I think you have it already. DA25, if you need it, please message Debbie and she'll supply it to you. This notebook, it will introduce us to TensorFlow, how we set up models, and then a couple of other concepts. So also saving loading, also early stopping, and also Gradio. So, in a lot of programming languages, when you start out in the language, you want to do stuff like do a hello world. Definitely people have done that in Python. So in Python, we want to hello world. Right. And then people do this in C, etc., etc. The equivalent version of doing this in TensorFlow is doing a regression, right? Because a regression is the simplest, easiest, most straightforward calculation you can do. This is the easiest solve we can do with our neural network. This is so simple that the design of our network will not even be this. It's just going to be one green node on its own, which is ample to handle the input and the output that we are going to do. So that one node will do the whole calculation for us and give us our result. So imports, first of all, you need to have these before you can do anything. We import TensorFlow, which is the new one for deep learning. NumPy you're all familiar with. And then we bring in Keras from TensorFlow. Don't worry about these warnings. Warnings we can always skip. As usual, typing TensorFlow dot every time would be a nuisance. So we alias that as TF, similar to how we do many other things. And then here's how we go about doing that neural network. So here is that neural network. We declare TF Keras sequential, and this is that same dense layer that I was looking at just now, right? So just one dense layer, and in this one dense layer we will have one node. So our whole model design, such as it is going to be just this, just that. This on its own is the entirety of our very complex deep neural network design. Right, so that's it. That's our whole neural network. Nothing. So this is technically not even a deep neural network, right? Because it's just the one layer. So, but this will probably do a pretty good job at what we are going to task it for. So here's our one model, and then we would want to do some. So we have to compile it. So this is the compile that we run. Here's stochastic gradient descent. I should take a moment to talk about. So, although it's fine for this model, because this model is very simple, usually, and particularly for Capstone, those of you doing deep learning projects, this will not be the optimizer that you start out with. You may finish your Capstone in SGD, but very, very, very much more commonly, where is my optimizer? Much more commonly, you will start with this one, right? You would start with the Adam optimizer instead. Why Adam first and then SGD? Adam has very, very sane defaults. These parameters, don't worry about them. Or rather, I can't cover them now, I apologize for that. You can read about them, it's fully documented here on the Keras page. These defaults, assuming you have a reasonable enough data set and relatively sophisticated enough model, will probably get you to 60, 70, 80% accuracy without you having to touch or fiddle or adjust anything. The trouble then is when you want to go up to 99.999% plus accuracy, then you do need to switch to stochastic gradient descent, and these defaults are awful. And so, a pattern that we see happen very often is you prototype in Adam, you get 80%. Okay, this is great. We need to get to 7 nines for production. Okay, I guess I'll do it in SGD now. You switch to SGD and immediately you drop to 30% accuracy. Then you have to start doing things like activating the Nesterov momenta, adjusting the clipping, adjusting EMA, doing all of this other stuff. And then as you tweak it, you gradually, first of all, take a week or two to get back to where you were at Adam. Then you spend more time to try and knock out that final top efficiency. Just an advisory note for when you're doing your capstone: don't start with SGD, start with Adam. Go on to SGD if you like to finish it off, but don't start with SGD. Here, it's okay to start with SGD, it's fine, because we're not doing a very complex problem. So here's a bunch of x's and y's. As the markdown says here, this is simply points on the line 2x, y equals 2x minus 1. So, minus 3 times 2, minus 6. Minus 1 times 2, minus 2. Minus 1 is 3. 0 times 2, 2, minus 1, minus 1, etc. all the way up until the 4 times 2 is 8, minus 1 is 7. Okay, so then we train the neural network by feeding it this data. So dot fit in Keras is very similar to dot fit in scikit. We feed it our x data, our y data. Here we say how long we want to train for. Here in this notebook, it's set at epochs equals, and then they put in a value. In the next notebook, you'll see a different pattern. The other pattern is this one, where you declare epochs as a variable, and then in the dot fit parameter, you just declare epochs equals epochs. This same thing equals same thing pattern repeats quite often in TensorFlow models, so I'll point them out as we keep going. All right, so 300 epochs, very, very fast. Even on CPU, this will be very, very fast. And then you can look at the summary of the model. Usually, you can call this summary immediately after doing the compile. At the moment, Keras is a bug on the latest version, so you have to train first before you call summary, but it's fine. It shows you your overall model, right? So our one dense layer with the one node, like I said, here's our full diagram of our very complex model. 20 bytes of memory in total params, of which only 8 are trainable. Oh, it's fine. Okay, so how does this model do now that we've trained it? Let's call a prediction. So we predict on 10. We know that the real equation of the line and all the other data points align to 2x minus 1. So we expect 10 times 2, 20, minus 1, 19, but we do not get 19. We get 18.897726, or when you run the notebooks yourself, some other 18-point value. Why does this happen? This happens because when you have, these data points and you are training the model, oops. I should probably go back to black for the axis. There we go. When you have these data points and you are training the model, so I mean very, very roughly, oops. I'll do the line, then I'll fake in the points. Alright, so there's a minus 1 and a 1 and a 0 and a 1 and a 2 and a 3, etc., etc. And then this 10 is supposed to be 19, right? So this is supposed to be 10, 19, but we don't get there. We never actually reach that point. Grab the eraser here. Why don't we reach that point? How come instead of giving us a clean 19, the model ends up predicting this 18.8 value. The reason is, this I should change the color of that. This hypothetical point that we are declaring up here, yes, it is true that we have supplied all of these other points, and yes, it is true that these points do resemble a straight line, but the model has actually no idea of knowing what does happen once you move beyond these points. So it is possible, not likely, but possible, that maybe our actual function is something like a sawtooth. And it is possible, again, not likely, but possible, that maybe our function is some kind of complex thing that does something like this. And there's literally an infinite variety of possibilities for this sort of thing, right? So there's all sorts of ways the model could behave lower than x minus 1, and there's all sorts of ways the model could behave after the final data point, which was x4, right? And so there's literally an infinite number of these possibilities. That doesn't mean that these infinite possibilities are weighted equally. They're in fact very, very suppressed. The model does think it's very likely that we have given it a straight line, but it cannot guarantee that. And because it cannot guarantee that, it doesn't give you a clean 19, it gives you this 1889. And this is foundationally important because you must understand that the DL model will never give you a clear absolute answer. It will always express things in terms of probabilities or likeliest values. So this is the value that the model thinks is likeliest to equate to x, for y at the value of x equals 10. That also is an important concept. So does anyone have questions at this point? All good? Okay. So then, that's it for this basic notebook. The next part is saving and loading the model. So I'll just quickly talk through the code for this. So saving and loading the model, do not use what's in the lecture slides. Do use what's in this notebook. You need to import these functions, save model, load model, from Keras models. And then once you have imported them, you can use them. So load model, if you point it to a model file on save model first. So save model, if you provide a file name, you can provide a path as well. That will save your model to the path on the system. H5 used to be the format used, but now we've switched to the .keras format. Loading models works the same way. You point at a path, it loads the model. Here, this value is different because I retrained that model just now. But if you, in fact, I'll just rerun the whole thing. Let me kill this notebook. Oh, yeah, this notebook is fine. This notebook did finish training. Okay, we'll come back to this. Oh, it hasn't. It's still on epoch 10. Oh, that's funny. Okay, we'll stop this one here. We'll put it out of its misery. I'll disconnect this runtime. But I'll keep the state because we'll talk about that in a second. All right. So retraining, and then saving and reloading. So here, once I run through the 300 epochs, it won't be 1887 necessarily anymore. It might be something else. Okay, it's 1883 now. But if I save the model and then load the model, you do see I get the same value, which makes sense because these are the same weights. So with the same input, they will make the same prediction. In my classes, everyone tried that activity of swapping the models around and the values around with everyone else. You also, if you take someone else's model and call a predict, you will get the same values that they get. Okay, so that's how you can... Yes?
Can I just check with you one thing?
Go ahead, Navid.
Is there a way of running the Jupyter using your own GPU?
Yeah, that's what I'm doing here. So you see I'm running on localhost. But to do... yeah. But to,
okay, sorry, not on Colab, right?
No, I'm running this one on local.
Yeah, no, so you can't do that on Colab for your local GPU.
Run a notebook on Colab with your local GPU. No, you can't. But you wouldn't need to because you have your own GPU.
Okay, sure.
Yeah. One thing you can do with a local GPU is you can publish Jupyter as a server, and then people on your own local network, so people in the house or in the office, can access your GPU through Jupyter, which is an interesting application. And let me talk about this again a little bit longer. So if you do want to get your own GPU and build your own deep learning setup, a great guide to doing that is by Dr. Tim Detmers. And he has this blog post that he, updates periodically. Wonderful guy. You can reach out to him on Twitter. He is very, very responsive. He has good guides about, how to effectively and efficiently spend your money to get, the GPU that will help you out the most. So lots and lots of answers, lots and lots of questions. Again, it also deals with Intel versus plus AMD versus NVIDIA. Why doesn't it work? The reason is the software. NVIDIA has years and years ahead of the competition on the software front, which they are definitely reaping the rewards for now. Because, it wasn't guaranteed. AI, when they started investing it in 2012, that is in the middle of the last winter. So it definitely was a gamble, but the gamble has paid off. All right, so this is how we can save and load the model. This is how you can stop the model training early. So here's a new model, same design. I just called it Model 2 to differentiate it. This one I compiled with a different optimizer. So, like I said, not necessarily the most accurate at the end. This is how you can do the early stopping. So this class, hopefully everyone did OOP in Python for Python 101, or at least got to read it in the extra material for Python 101. This class calls back to the Keras callback class. So in Keras we have a whole callback API. You can do all sorts of things with the API. So you can invoke TensorBoard, you can stop the model early, you can schedule the learning rate to change as you train the model. There's a lot that goes on. But for just early stopping, where am I? For just early stopping, you can do something like this. So you can make a class. I happened to call it early stop here, but you can call it whatever you want. Any valid variable name in Python is fine. This code is what will do it for you. You can lift probably all of this code yourselves for any purpose if you ever need a callback. The one thing that does change is this thing. So in the logs, the 4 parameters you have available are loss, accuracy, validation loss, and validation accuracy. So loss, generally you want to set to be a less than value. Accuracy, you just generally want to set to be a greater than value, which makes sense, right? You want to train until the accuracy is 85 or more. Or you want to train until the loss is, in this case, 0.03 or less. So here, I created this callback. I instantiated it as a variable called callbacks. And then later on, when I did the fit of the second model, same data set, this time 1,000,000 epochs, which would be a while, even at a few milliseconds per. And then I specify the callbacks as this as a list, right? You can have multiple callbacks. So, but I did callbacks equals callbacks, which is just this early stopper. The early stopper then, hopefully, there we go. We reached 1471. We hit that 003 loss figure, and we stopped training early, which saved me about 1,000,000 epochs of training. So very, very helpful, very, very useful to do. This again, you can, if you ever need to do an early stop, you can just take this code. Just make sure you set this parameter correctly in line 3. And then the final thing is building an interface for Gradio. So here we sadly don't have enough time to dig through this entirely. This should work actually. Yeah, it actually does work. I mean, it'll probably get overwhelmed when you all click on it, but I'll share the link. So this is that interface. Without knowing, any front end, without having to learn any HTML, any JavaScript, anything like that, you can take your model, make it available over the internet with a, at least a decent enough interface, if not an attractive one, and then other people can access your model and use it to make their own predictions. So how did we do this? Whereas, I said it takes a week to do it in TFX. In Gradio, it's really, really easy. The library provides a lot for you. please take this note, and please read all comments that I make in my notebooks. All comments I make in my notebooks are, for your benefit. So if you're running on Colab or Kaggle, you do need to install Gradio first. Gradio is not included in Colab or Kaggle. I happen to have Gradio installed in my environment, so it's commented for me. For you, you may need to uncomment it when you are running, something like this. Also note for everyone, Kaggle seems to be having Gradio trouble this week, or some sort of Gradio allergy. So if you are trying to do Gradio stuff, try and do it on Colab, for this week anyway. How does the code work? Just very briefly, we bring in Gradio. You have to create a predict function, which is this function here, which is still our regular model.predict. Here I'm returning index 0 of the prediction, mainly for the benefit of lay people. So lay people get scared by square brackets and other things like this. I just want that number out. So this is a list of a list, a one element list containing a one element list. I take index 0, which accesses this inner list, and then I take index 0 of the inner list just to get the numeric value out, which is why my prediction is that one. Is everyone trying the link? Is it working? Are you all getting inference out? Last link I put in chat, the 08830cc. You can all click it. It will probably get overwhelmed soon because Hugging Faces servers are not the most robust, but at least a couple of people should be able to get inference out of it. Okay, so you declare a predict function. Then this is the main thing. So you declare Gradio interface class. You specify what your function is, which is your predict function right above. You specify what your inputs are. So here I specified a slider. Specify what your outputs are, and then write a title and description. So as I mentioned, there are so many inputs available on Gradio. We have lots and lots and lots available. So you can read the Gradio docs, which I did link it. Oh, no, I did. You can read the Gradio docs to see what is available for you to use as an interface that people can interact with. So you can make a button available, and then they can click on the button. You can make a drop down, you can make a color picker, file picker, you can make an image drop down so they can just drop an image on it. All sorts of stuff available there. Everyone done with the model? Okay, I'm going to shut down this notebook then, just on account of my VRAM. Okay, then once you run this, you do interface.launch. If you specify share equals true, even on local, it does get shared to the public. If you run it on Colab, it automatically becomes share equals true, and then you get this link that you can run. The link does depend on the model being live somewhere. So when I shut this model down, for instance, right, I close and halt my notebook here. Notebook is down. If you now click that link that was posted, now that link will error out. It gives you the no interface running now. It was this link here, right? So I brought down the notebook, now the interface is done. Okay, that is the end of Module 2 TensorFlow. I will pause again for questions.
Sure.
Yeah, go ahead.
Yeah. So I wanted to check on the early stopping. Is it a package? Do we need to install it?
No, it is included in Keras.
Okay. All right. Thanks.
No problem. Other questions? All okay? Okay. So we'll do CNNs. I'll run through the CNN notebook and the extractor, and then that's the end of our revision for today. Okay, so CNNs, this is module 3. This is the big meaty module because this is, most of the assessment as well. It's quite a lot of theory that goes on here, but we'll try and do this in 20 minutes or less so I can get onto the notebook. All right, so CNN architecture. Here's AlexNet again. This actually happens to be two CNNs piled on top of each other running in parallel to really show it at a node by node level. Here is that example from the Asimov Institute. So this is a DCN or a CNN or an ANN, a CANN. And you will notice that there is actually only a very, very subtle difference between this and what we have here here for the deep feed-forward network. In fact, looking at it, all that has changed from up here on the top right of the deep feed-forward network and this DCN is that we've stuffed in these convolutional layers, these pink layers down here. And so that's a pattern that you will see repeated again and again, also in deep learning. If you have some specialized task that you want to achieve, then invent a new cell or a new layer type that is specialized to that task, and then build a new model, employ maybe some deep nodes and also that new layer that you designed. And everyone who finished module 4 already, you'll know that this happened for our RNNs, where we have these LSTM, GRU modules, nodes available. So it's all really a question about special layers when it comes to the application side anyway. When it comes to the research side, it's definitely special layers because you're developing your own sort of thing. What is actually a convolution? That's sort of a strange word, related to revolution, related to evolution. What happens is we pass a matrix or kernel over a raw image, and then we adjust the values of that image based on what the matrix is. So say our matrix is this one, the identity matrix. Multiply this by a base image, you get identity. Nothing changes. Say this is our matrix, the Lanczos sharpen. You multiply this matrix by an image, you get a sharpening effect. Right? This is sharper looking than this original on top. So you multiply a fractional value, you get a blur. So you do one of these detect ridges and edges. So either the horizontal or the vertical features start to pop out, and you can see this outline of our subject of interest. CNNs are all about extracting those edges and features. And so I mentioned this also to my cohorts. Type this in. Where am I again? I know I have the link here.
Dog versus cat classification.
Oop, not that one.
Okay.
No, not what I wanted. Okay, I'll dig it up. I know I have it in one of our channels. Yes, here we go. Sorry about that, Evan. Surprisingly difficult to find that link on YouTube search. Okay, so here, this is a Kaggle video about the concept, but we don't need to watch the video. I mean, you can watch the video if you want. I'll give you the link. But what I'm interested in using this video for is this image from this point in it. And this image is this one. So this is clearly depicting what I mean by edge and feature when I talk about edges or features, or when any machine learning engineer talks about edges and features. So an edge is literally this, literally an edge, or a point in the image where we see a transition from one color state to another, or we see a primitive of some sort of shape, like a line at various angles, or we see just a patch of one piece of color, right? And this might be very, very small. It might be just a matter of a few pixels across. But from these primitive edges, if we assemble them together, then we get the intermediate features of an image. So in the case of an image like a whole car, we get features like a wheel, or a window, or a door, or the bonnet, or the rear. And then these intermediate features, when they are put together, they can assemble, the whole subject of interest. So you get a whole car out of parts of the car, the features, and you get the parts of the car out of the very, very primitive fragments of the images, the edges, right? And CNNs excel at extracting edges and features from images, which is why we use them in computer vision tasks. So this is an example of a series of convolutions that happens And you may notice that, say this is a mask detecting model. You may notice that, okay, well, this is all right, but it seems like only that one and that one and that, or maybe that one, are actually doing a good job of giving us edges and features. It seems like all the rest are kind of awful. It's not the case that they are bad in the absolute or in the moral sense. They're still doing a great job of pulling edges and features, and I'll prove it. So let's take this one, which I'm sure you will all agree is a horrible job of making the face mask very, very obvious, right? This one on the top right. Let me put this here. And then let's find out the edges and features that the model has extracted for us for that one. So this image, let's blow it up. Right, so there is quite a lot actually that is very, very distinct down here, right? We have a huge dark patch down here, huge dark patch down here, and quite a big bright patch down here. So we've got those features. What are those features? In the original image, those features happen to be the red sleeve on this t-shirt, this orange towel, and this bit of blue tape on the washing pool, on the drying pole. Now you may say, well, I'm not interested in any of that. The machine has no idea in knowing what you're interested and not interested in. It will extract every edge and feature out of the image, and it will assemble those in its library of convolutions. And this will come into play later on. So we can expect probably that the majority of the convolutions we derive out of the model will not be generally suited to our particular purpose, right? Maybe if we were very interested in getting the fringes of the t-shirt, then the others would be good. Speaking of which, right, talking about the ones that we considered good convolutions, look at this one here, right? The lady with the mask, very, very clear, but do you see the edge on the t-shirt? No, you don't, right? So the different convolutions are suited for different purposes. And it's very, very likely that the majority of convolutions will not be aligned to one very specific purpose, which is usually what we are after when we're doing a classification task. So here is that layout of how the convolutional layers are spread out. I am going to cheat here and recycle what I did with cohort 2 for how this equates to code that we're going to see very, very shortly. So in just a moment, when we look at the canonical or the documented CNN that the TensorFlow people put up, there's a bunch of code down there. That bunch of code corresponds to a series of equivalences in this image. So in this image, you'll notice the input is this image of a car. If you look carefully, there seem to be 3 sheets here, right, stacked on top of each other. The reason for this, same thing here, right? 3 down here, what? This floating 3 is the number of color channels. So if it's a full color image, that means there's a channel for red, and a channel for green, and a channel for blue, which means there will be 3 color channels. This explains why there are 3 down here. Then here is this convolution and pooling layer, right, equivalent to what we have down there. And then after we convolve and pool and convolve and pool and convolve and pool, we still have a 2D image, so that needs to be flattened into a 1D array before we can feed it to the dense layers. Then the dense layers will output to the output layers. Notice here the outputs, we have 1 output for every class that we are classifying. So if we look at how this is equivalent to the code, or will be equivalent to the code later on, here are the correspondences, right? We have a scaling layer that will take in this input. Notice this 3 down here in the Python code in the left. You have to be careful of color. So 3 full color, 3 color channels. Convolution and max pooling layers is this purple equivalence down here, right? So that's how you implement that in Keras. The flattening layer is literally this flattening layer in red. We have 1 dense layer here, and then we have a dense layer at the end for the output. Notice the output layer corresponds to the number of classes that we are classifying, which is why I triple underlined it. So this is just, on the right, a design, right? And this design has this implementation here on the left in TensorFlow, but you could also implement a CNN in PyTorch. You could also implement a CNN in another language, like Julia or in C++, right? There is no, it's not as though it's exclusive to TensorFlow and Python. I do need to make that very, very clear to everyone. Okay, so then, we talked about convolutions to extract the edges and features. What is pooling? Pooling is where we shrink this image. How do we pool? We pool this way. Either we max pool and we divide the image into segments and then take the maximum value per segment. So max in the green is 100, the 100 goes down. Max in the red is 184, the 184 goes down. These are all 12s, the 12 goes down. This has a 45 as the max value, that goes down, giving us 100, 184, 1245. This is now a 2 by 2, whereas that used to be 16, right? 4 by 4. Average pooling works the way that the name suggests. We sum up each section and then we take the average. So the average here in the green is 36, the average here in the red is 80. Again, this is all 12, so the average is 12. This adds up to 60, so the average is 15. Right, so that's how we pool. As to why we pool, this is why. So there is a very, very big risk, especially when you are dealing with color images, that the numbers you are going to have to process are simply going to be too big. And then you'll end up with, say, what we call an exploding gradient. So I would say, for example, right, we have, say this was really high-res, full definition. We would be talking about, what would we be talking about? 1920 pixels wide by 1080 pixels tall by a color value for red and a color value for green and a color value for blue. This is enormous, and that is one image, right? Huge, right? Over a quadrillion, right? Because a billion is 10 to the 9, and then we're beyond 10 to the 12 at the moment. So with these 34 quadrillion parameters just for one image, you can see that this becomes a problem even on modern systems. So that's why we max pool. At least in some of those parameters, like that early 1920 times 1080, we can reduce those a bit. The color factor also is very big, so we'll talk about that later. The other problem is this problem here on the right, which we don't have on CNN so much, but it does happen in other neural networks. If your gradient values are very, very small and close to 0, and you start multiplying them together, they might have that tendency to vanish. So both of these are problems, and machine learning engineers have developed techniques to deal with them. That's almost it for CNNs. I just wanted to mention one last part. We shared that model saving and loading before. You can also do this model saving and loading for CNNs. And so there are CNNs that have been trained on ImageNet for hours and hours and hours on very expensive GPUs by very, very highly credentialed PhDs in top institutions and companies all around the world for AI. And all of these are available to you for free in Keras. So again, looking at the documentation that we have available, there is, this part will always break for me. Here we go. Tons of models available for you. Many, many more than I actually fit on the slide. And a lot of these models, like I said, have been trained for hours on huge data sets. So you can imagine then that the library that they have of edges and features is extremely robust, right? Extremely robust. I mean, going back to that article, there was millions of images in ImageNet. If you can imagine a very, very complex CNN training for hours or days on that data set, it would have pulled a ton of images out, a ton of edges out, and also a ton of features out, and would be extremely powerful. And so the way this is usually invoked is this way. You bring in your application, you freeze the weights on the imported model, right? Because you don't want to retrain all that precious training that already happened on ImageNet. You don't want to mess that up. So you can freeze just those weights, and then you add a couple more layers that are trainable. So you have those for your specific application, like grasshopper versus locust, or butterfly versus moth, or whatever you were doing. And then the model has a benefit of all of that ImageNet training, as well as a little bit that you're specifying here, and then becomes very, very powerful at these tasks. Okay, so that's a CNN lecture. Questions before I jump into this notebook. Anybody? All okay? All right, then let me jump back to general here. Let me see if I missed anything. Okay, didn't miss anything. You can drop questions in chat, everyone. I'm happy to take them at any time. Very glad to. All right, so this notebook, like I mentioned, in general, when I posted it, it is a link to that documentation that exists on the TensorFlow website. You must understand this notebook in complete detail, because knowing this notebook inside and out will really help you anytime you need to do anything related to a CNN. It is a great introduction. It is a little bit long, so it is. So we'll spend a bit of time walking through it and explaining what is happening here. Again, I'm going to accelerate slightly just on account of time. I do have to do the evening class. Okay, so actually no. Okay, when we get to training, we'll talk about GPUs. So imports, TensorFlow again. PIL is the Python image library for us to do images inline in the notebook, plus Keras stuff for getting in the layers. This dataset is about flowers. There are 5 classes, so it's going to be a 5-class classification, which again, going back to the notes, means we will have 5 nodes in the final output layer to accommodate all of our different classes. This cell here is where we download the dataset and extract it and point the notebook to it. So dataset URL is set. The get file util will download it. It comes in the format of a .tar, which is a Unix tarball. We will extract it, and then this here is pathlib, setting the path to where that dataset exists now on the system. On Colab, when you run it, you will have, because this is an instance that is not local, because it's remote, you have access to things like the Colab file system there, so you can download and upload files. Here I ran it locally, so it went to somewhere in my local storage. We are taking the length of the list of everything in the data directory that is in any of these subdirectories, and then within those subdirectories, that's the first glob, any file that ends in a .jpg. So it tells us that there are 3670, and then we use PIL here to look at certain of these images. So a couple of samples from roses, a couple of samples from tulips, fine. Then we have to convert this from images into something that we can feed to the model. You will notice that these images are not at all the same dimensionality. This is a problem, so we need to homogenize them, or we need to change their sizes to be the same, so we can then feed them to the model. So here we set some parameters for this. We set a batch size of 32. That means when we do the forward pass for the epoch, the images will go in 32 at a time until all of that split of the training set has gone in. We decide that we want 180 by 180. It's a reasonable enough size to get a good number of edges and features out. Other common sizes you might see are 224, 224, 9090, 4545. Various sizes are available there. 2424 also popular. All right, and then here is how we do a test train split for images in Keras. This utility, image dataset from directory, if you point it at the root not the root directory, the main directory that holds all of the labeled subdirectories for your classes, it will do a lot of the work for you. So all you need is to have your data organized such that all the images are in directories that have the label, and that will take care of the whole task of labeling for you. So line by line here, specify the data directory, specify what the test train split is. Notice we only specify the test here. So here, since this is the training data set, we take this to be implicitly the inverse of this, right? So if the test split, what Google calls validation, is 0.2, the training split is going to be 0.8. We set a random seed here just to be reproducible. You can set a different seed or remove it. Here we set the image size equal to the image width, height and width we specified earlier. And here's that paradigm I showed you before. Batch size equals batch size, right? Nice because it's kind of convenient, but it does mean you have to specify the batch size down here. rather than do a batch size equals 32 in there. As you get used to the syntax of TensorFlow, it'll be easier and easier to do this sort of thing. So you do batch size equals batch size, epoch equals epochs, callbacks equals callbacks, etc., etc. So here's our 80% of the data for training. Here's the same thing, the 20% for testing. The only difference between the arguments for these two is one we specified as the variable trained_ds, this one we specified as the variable val_ds, and we said this subset is validation, and that subset was training. Image dataset from directory takes care of all the rest for us and gets it ready as a NumPy array to feed to TensorFlow. We also want the class names. They appear here as an attribute of trained_ds. So here are all of our class names, which are simply the directory names that we had. This code just is matplotlib to show some of the images. This code is just looking at what's happening in the batches. So each batch is 32 images. Each image is 180 by 180 pixels with 3, there it is again, for the color channels. Same thing that is said down here in the markdown. This is an auto-tuning section, which you can ignore if you like. Later on, for the next task, this is something that should be removed. This has nothing to do with the model. This is just the data optimizer. This is how you can standardize the data. So remember, we were talking about max pooling being one way to combat the exploding gradient problem. The other way is to combat these multiple 255s. So we scale them down to the 0 to 1 range for red and green and blue. And this really helps out a lot. So we call layers.rescaling and we divide through by 255 is one way to do it. Or you could declare a lambda and then use .map to map that lambda across everything. Generally, in the years I've taught, no one has preferred the second approach, but maybe you might. This approach is the one we'll take, but we won't use this variable normalization layer. We'll actually declare another one for the models. So the first model is this one. So the rescaling, like I said, we're not going to use that normalization layer above, we just declare it up there. 3 pairs of convolution and max pooling. 3 pairs of convolution. 3 pairs of convolution max pooling. So convolve, max pool, convolve, max pool, convolve, max pool. Always in that order. You don't start with a max pool. You always start with a convolution. You always end with a max pool. So these are the pairs. Convolution followed by max pooling. Then a flattened...
Bishwa,
Yes, sir.
I noticed that it's increasing from 16, 32, 64. Is it always increasing?
It can do, or you can change it. So what's happening there is... go back to the layers API. So 2D convolution layer. What we're specifying is the number of filters that we are passing over the image. So the more filters we have, the more features we can extract. The reason it's increasing is if we had the larger number earlier on, again, possibly we might run into memory problems. So safer for us to increase the filters later on when the image is smaller. But it doesn't have to change. You can try, and I do encourage all of you to experiment with adding on more pairs and then doing something like a 16, 32, 32, 64, 128. Give that a shot. See if it works out better for you. It's good to experiment with these things and good to build up a set of your own practices. For example, something I do is I usually sneak in a 10-inch somewhere in the model. This does have the effect usually of giving me a small boost in accuracy most of the time. Plus it's easy to undo later on if it turns out to be a regression. I can switch back to straight relu. Good question. Other questions about the design here? All okay? Okay. So here's our compile in that case with Adam in this case. Here when we specify the loss function, this loss is passed categorical cross entropy, whereas in the earlier notebook, it was a regression problem, so different loss function there. Usually use pass categorical if you have more than 2 classes. If you have 2 classes, there's binary loss functions available. Alright, so here's this model, which is significantly more complex than what we had before. Almost 4 million parameters, almost more than 15 megabytes in size. This is a perfect example of that trade-off between interpretability and accuracy. Whereas before, with a single straight line, we can declare any point at x and you could read off a value for y given the line function. Here, it would be hard pressed for anyone, even Jan LeCun, even Jeffrey Hinton himself, to go into this model and say, well, okay, at this layer, at this point, this convolution is contributing around 0.02% to overall accuracy. You do not have that insight anymore. The trade-off is this model will do a pretty good job of doing the classifications later on. So that is a trade-off that is made. We train the model by calling .fit. Here's that epochs equals epochs pattern that I said before. This one doesn't have a callback. You don't have to have a callback every time you declare. So here we specify the training data set. The validation data set, you notice you do have to declare. So do keep that in mind. So like I said here, all right, so here, 12 millisecond per set on local. We put this one out of its mercy. What is going on down here? How did we get to this problem? And what is wrong with CPUs? There's nothing wrong with CPUs. What it is that the two pieces of hardware are designed in different ways and are designed to solve different problems. So CPUs are focused on latency, which is they want to do one task very, very, very quickly, which is a good idea for the central processor of your computer. In contrast, I can show this. So a very reasonable, very modern processor released within the last year, still available. You can buy it on Shopee if you want. For I don't know why my prices are in ringgit, but you can buy it for around this. Oh no, that's the i7. Check the similar price. Yeah, there we go. This looks more reasonable. Yeah. So yeah, around 1,000 or around 900, depending on which speed you get. Really good spec sheet. Top 24 cores here. Top speeds almost touching 6 gigahertz. High cost, very modern, very reasonable design. In contrast, I can show you the GPU that I took my TensorFlow certification exam with, which is not available anymore, so we're going to have to go on Carousel to dig it up. Carousel Singapore. And here, they were still available last month. I hope they're still available this month. And while that's there we go. Oh, prices. No, price is still the same. Okay, so between $60 to $50. This is my literal model. You can buy this state-of-the-art 2014 GPU for which is $50 compared to 1,200. Big difference. But I can promise you that this GPU will get results that are not much worse than these values, maybe 20 milliseconds or 22 milliseconds. And I can promise you that this CPU, forecasting 4 digits, will still deliver performance in around this region. Why? Let's look at the NVIDIA specs. This is the 970M. Did we lose it? Okay, here we go. I'll just steal the MSI specs. Okay, so this machine, this component, a lot slower overall, right? 1241 megahertz, barely scratching a gig, compared to 6 gig, right? So like we said, CPUs prioritized for latency, designed to run one thing very, very, very quickly. But the trouble is, if you look at this CPU core count, and Intel in particular is playing this game these days of giving you rubbish cores mostly, and only a couple of good cores, and you compare it to this core count available down here. Where am I? MSI, why do you not list these things? There we go. Alright, that's no good. Galax will give us good specs. Hopefully, because they're Japanese. There we go. Compare that to this value. It's out of the water, right? And my 3060 has even more than this. So, although these cores are slower, I have orders of magnitude more of them, right? 1664 compared to 24. And although they're slow, the other thing you should look at in addition to the core count is the cache, or the memory available. So we have 36 megabyte here, which is good for a CPU, but this thing needs to push polygons. And so since it needs to push polygons, we have lots and lots and lots of VRAM, right? 32 megabytes versus 4 gigabytes. And so it's like, and Tim Detmers has posted this on Quora. In fact, let me find his Quora quote. Right, so they're all about the optimization, but this you don't have to read. I'll give you the link, but you don't have to read the whole thing. Although I do encourage it. The interesting section is this one, right? So this is like asking a truck to go down to the warehouse and bring packages for you. It is true that if we send the truck, we're going to wait a while because the truck is slow. But once the truck comes to the warehouse, we don't lose efficiency at all because there is so much data being brought over in the truck that we are saturating the reading capacity of the model. Whereas, here, say your CPU is a sports car, you are bringing like 2 boxes over. Yes, you're going up and down the road a lot more quickly, but you're not bringing in enough data that is being processed in enough time that, everything can be done efficiently. So, this is why GPUs are absolutely essential for serious deep learning applications. When I say serious, I mean either you are in grad school or you are a deep learning company or you're an AI company and you need to have access to this hardware. And even AI companies get into trouble when they don't have access to hardware. For example, the CEO of Perplexity said he was hiring a researcher, but he lost the researcher because the researcher expected him to provide thousands of A100s for the researcher's research, and the Perplexity CEO could not promise that. Okay, so GPUs essential, NVIDIA GPUs in particular essential because we need the CUDA framework, and particularly CUDNN, which is the deep neural network acceleration in CUDA, to make this happen. AMD is trying to catch up in software. You can read the Detmers blog about it. Intel is trying to catch up in software. In fact, Intel, there's a rage about that lately. Intel CUDA, there's a statement that I saw the other day. Yeah, there we go. Here's Gelsinger saying, the entire industry is motivated to eliminate the CUDA market, by which he means him and Lisa Su at AMD. But, like I said, NVIDIA has built this moat very, very deep and very, very wide. So it will be at least 5 years before these guys catch up. And when while they are catching up, NVIDIA is still moving forwards. All right, so that's a quick note about GPU versus CPU, and why even with a very, very expensive CPU, you will have terrible results at training deep neural networks, and why with even a cheap, out-of-date, old-fashioned GPU, not this one, let me find one of my old notebooks. So here's a notebook, I think from 2021. So definitely on that old GTX 970. There it is. I still have this GPU, it's sitting in my cupboard. This was something I was doing at IBM for face mask detection. And the dataset was huge. It was 11,000 high-resolution color images. And you can see, right? Even with that enormous dataset, even though this was an old GPU, it was still doing things in the order of seconds, right? Not milliseconds, seconds. But I've had my current GPU do the same task. It does it in about 15 seconds, but we're still talking about the order of seconds. If you take a CPU and turn it on this task, you'll be talking about multiple minutes at least to do it. So, one of the things you can do if you are interested is you could buy an old GPU. They do a pretty decent job. Just make sure the versions match. By versions, I mean the CUDA compute versions. That is out of scope, so we'll talk about that another time. Okay, so that's training-wise. This is this first model. Once it's been trained, we come down and we have a look at the results. So this is just a bit of matplotlib to see the results. It does pretty well in training, and it gets to this 0.9 accuracy. It does pretty well in training, and it gets loss very, very low. However, in the test set, accuracy kind of peaks at 0.6, and loss starts shooting up. So this gap between how it does in training and how it does in test is called overfitting. And overfitting in simple terms means that the learning power of the model has been adapted not to the features that we would consider useful in the dataset for the task that we want, but rather noise in the dataset. By which I mean, remember the model is extracting every edge and feature. So say in this image of a rose, this here is all of our rose-related content. And we would like the model to learn things like the arrangement of the petals and the shape of the stem and maybe the leaves and the thorns. But the model has instead learned the color of the background wall and this drain pipe down here and this watermark that the Google engineer forgot to take out of the dataset. And so when a similar image comes up with a wall and something like this, the model will say, oh, that's a rose. Much like that model from slide 1 where it sees a bright day and it's like, oh, this is a tank. So same thing. Model is maladapting to noise and not picking up the useful edges and features. So we have to combat this. And fortunately, there are several ways to combat this, starting with the fact that machine learning, deep learning, still part of machine learning, means we are still bound by all of this, which means that since what happened here is we got a bad P, we can probably improve by giving the model more E. So how do we give the model more E? We'll take 3 approaches for this model. First approach, we will augment our data. In Keras, you have 8 different types of layers to do this. You can flip, rotate, zoom, crop, scale your images. If you do, a variety to say this dandelion, it will look like this. To all of you, this probably looks like the same image, but to the machine, remember it is very, very literal, very, very precise. So we have changed the pixels here, which means that that tensor of the XY coordinates and the color tuples is going to be completely different for all 9 of this. So it is like a 900% boost in E. Now, that said, remember when we talked about this here, 900% increase in E doesn't mean a 900% increase in P. Maybe it's like a 2% increase in P. But an increase is an increase. We will take it. It is good for us to do. The other increase in E, I'll skip a second, I'll come back, is that we'll up our training time. So before we trained for 10 epochs, now we'll train for 50% more training time. And then now I'll talk about this one, which is the mysterious one. Dropout is where we throw away some of the output we get. And if you remember from the lady, doing the with her face mask and the other convolutions that we're doing, the t-shirt sleeve and the drying pole and all that other stuff, it's pretty much guaranteed that most of our convolutions in this model also will be bad. So we'll throw them out. We'll throw out 10, 20, 40%. Here it's 20%. And we'll just get rid of them. After all of the convolutions and max pooling, after all that work of pulling out the edges and features, we'll just get rid of them and keep 80% of the features, because it's likely that the majority are bad. Statistically, we'll probably throw away the bad ones and keep the good ones. Again, bad and good not in the general sense, but just for our specific purpose. So these are our three techniques that we're going to use to combat the overfitting. One, we augment the data set. Two, we're going to drop out some of the layers and some of the output from the convolution layers. Three, we will add 50% more training time. So doing this, training this model again, now we get lines that are closer to each other, which is better. That is a happier result. We are, it generally seems okay. It may not be our absolute ideal of, what things should look like. Again, bringing this notebook back. May not be our absolute ideal of things sticking for hundreds and hundreds of epochs in close proximity, but, decent enough for this introduction. And so that's our approach to solving overfitting. And then here's how you call or predict on an image. This cell also is important, mainly because a lot of these conversion utilities here, later on, if you're trying to do Gradio to do an image drop, it's good to adapt some of these things. Now the final notebook I want to cover is this notebook here, which is the CNN extractor. And I know you may not have done it in DA, but my classes did it. And it involves going over this notebook and bringing out just the code that is essential to run, to design, to download the data, load it, design the model, compile it, train it, and make a prediction. And not all of the code in this notebook is necessary for that. So there's headers on this one for what you should bring out. I'm not going to cover the answers for this one because this really is something that you should practice on your own. You should go through the documentation on Core. You should try and run it yourself on Colab. You should experiment with the models to see if you can get more accuracy. So it's a great idea to go in and do stuff with the convolution layers, or maybe add another dense layer so you actually get a deep neural network, or 3 dense layers. Why not? Tweak and adjust and play with these things, because that is the whole job of machine learning engineering. It is knowing what hyperparameters are available to you and adjusting them such that you can get an optimal result in the either maximizing the accuracy or minimizing the loss, or hopefully both, in your models. Okay, so this, I will read through the header. So when you are doing this extraction practice, you'll need a code block to import libraries. You'll need a code block to acquire data. You'll need a code block to load that data and pre-process it. So not just downloading, untarring, you'll also need to load it as an image data set. You may want data augmentation of that image data set. You may want to add a dropout layer, which you don't actually need to do here. You can do that in the model. Then you can do the model. You should use the better model from the notebook. So a couple of errors I saw as people do this is they just bring over the code wholesale. So don't bring over the code wholesale. If something has nothing to do with the training of the model, do not extract it in this extraction practice. The purpose of the extraction practice is that you extract only what is most essential to designing a CNN, and then you can use that notebook as your template or your blueprint, later on when you're trying to do your own CNNs for various purposes. Okay, and then you design the model, compile it, train it, do the graphs for evaluation, and run an inference. Okay, like I said, I'm not going to cover the solutions for this. I will make the solution file available. I think it already is for my cohorts. Day 25, I will leave a copy with Debbie. Okay, 2 hours, 13 minutes, 42 seconds. Near the end here, does anyone have any questions before we stop? So I have been recording the whole time. So those of us who haven't made it, or those of you who want to watch this again, I'll try and get it up on YouTube as an unlisted. I'll make the link available to all 3 of your batches, hopefully by tonight, if not by tomorrow. Anyone? Anything? At all? Anything at all? All okay? Oh, yeah, and I see one question. Okay, I'll address that question later. Okay, if not, thank you for coming for revision, everyone. I hope you found it useful. Remember, particularly when you go to assessment for our SCTPs, you must be firm on your concepts. And all of our concepts in this class do build on each other, which is why I introduced them in the order that I did. So you have to be aware of where deep learning falls in the general scheme of things. You should download this textbook, which I'll give a link for as well. Actually, it's worth reading, the machine learning textbook. Then go over everything in the slides. If you want to follow up a reference or dig deeper, that's a great idea. So you should find out about Rosenblatt's life. You should dig into the Perceptron's book and find out why Minsky behaved the way he behaved. All of that is well worth doing. You should dig into ImageNet, and you should read the original AlexNet paper, which I'm going to also try and make available for everyone. All of this is good to do. So if you're sound on the concepts, then the execution on the code side is relatively straightforward, because everything will play into what you already understand from having covered the work and having done it already, right? So for example, that diagram of the equivalence between the sections in the slides and how the code is implemented in the notebook, right? All of this is very, very straightforward, right? Some of the names are literally the same, right? Flatten. So really, really make sure you have a firm grasp of the concepts. You're all on the Discord, so don't be a stranger. You can drop me a message, or you can drop something in your cohort chats. I will be happy to pick it up. Last call, any questions? Okay, thanks for coming, everybody. I'll see cohort 2 this evening, and for the rest of you, good luck with your assessment.